Okay, hello. This is our almost final lesson of the year. We have been studying for the past 2 weeks regular grammars, and we have seen that regular grammars are very powerful and generate regular languages, but there are many languages which are not regular. And can we describe those languages also with grammars? Yes, we can, but we need grammars with less restrictive rules than the rules of a regular grammar. So, okay, here we go. This is gonna be just a kind of a brief, superficial overview of this. Okay, well, in all of these grammars, we have a set of terminal symbols, which are really, this is probably not the best, well, this is what everyone calls them, but really the terminal symbols are just the letters of your alphabet. And the characters of your alphabet in your target language. And then you have the non-terminal symbols, which are built into the theory. And, okay, every grammar is a set of terminal symbols, a set of non-terminal symbols, a start symbol, and a set of production rules. And the only thing that differentiates the grammars from each other is the format of the production rules. What kinds of things are you allowed to do in the production rules? And every one of these production rules is always of the form, replace something with some other thing. And for regular grammars, I'm not going to go into this whole thing again, but basically you're always replacing one non-terminal symbol, a single non-terminal symbol, with something, and the thing on the right can have at most one non-terminal. It has to have a terminal. If there is a non-terminal, it has to be all the way on the right, and you can terminate with the null string, but then if the null string is your only terminal symbol, then you can't have any non-terminal symbols. Okay, so I'll assume we've just mastered that, so maybe I'll just, I'll just put like a check here, because we've already gone through those rules in some detail. What are some examples? I'll put some examples over here. We have simple rules that take a non-terminal and replace it with a single terminal. We can replace a non-terminal with a terminal and a non-terminal, but there can be only one and it must be all the way on the right. We can also replace a non-terminal with just nothing, kind of like that. And I guess that's just pretty much it. That's pretty much it. Okay, whew, good. Now we move on to the so-called context-free grammars. Okay, what's a context-free grammar? Well, all the rules are still of the form x goes to, but now over here you can put just like whatever. And the way to express whatever is that alpha is just, so alpha is meant to represent some string, and basically what we want to say is alpha could just be just anything. So just any combination of terminals and non-terminals, any number of them in any kind of order whatsoever. So the way which, okay, maybe this is confusing at first, but then you get used to it. The way of expressing this formally is by saying that alpha is an element of sigma union delta star. So take all the symbols of all the terminal symbols, all the non-terminal symbols, put them all together into one big set, and then the star generates, all finite strings composed of any of those characters, and so alpha is just one of those. So this is just another way of saying anything you want. So now suddenly we are free to do all kinds of things. So yeah, we can still have rules like x goes to a. We can still have rules like x goes to a, y, but now, suddenly we're free to have rules like x goes to ya. In other words, now your non-terminal symbol doesn't have to be all the way on the right anymore. It could be on the left, or it could be in the middle. So maybe x goes to like a, y, b, or something like that. Ooh. But also, we are completely free from our requirement that there be any terminal symbols at all on the right-hand side. So we may sort of linger, as we did early last week, when we were talking about linguistics, we may sort of linger in the theory for many, many steps, kind of generating more and more non-terminal symbols without actually making any progress in the generation of our final string, so to speak. So that is to say, you can have a rule like x goes to, x, x, y. So you can not only can you produce, not only can you have a rule such that the right-hand side has no terminal symbols in it, but you can have multiple non-terminals. Perhaps this would have been better seen with a couple different examples. So you can have like xay shows this is certainly a rule that would not be allowed in a regular grammar because there are two non-terminals. But in fact, we can have rules in which there are no terminals at all. So like the one I just said, x, x, y. And in fact, just any arbitrary string composed of terminals and non-terminals is allowed. So like, y, a, z, b, x, something like that. Okay, these grammars are called context-free grammars. And just by virtue of the name context-free, you might be thinking, well, okay, this seems quite powerful. Well, how much more power could there possibly be? And the more power that you might want is for your grammar to be so-called context-sensitive. And so the context-sensitive grammars, oh, and wait, one thing I quickly forgot to say is that, of course, every one of these rules, all the rules which are allowed in a regular grammar are also allowed in a context-free grammar. Thus, technically speaking, every regular grammar is automatically also a context-free grammar. And since we define a regular language as a language generated by a regular grammar, we also define a context-free language as a language generated by a context-free grammar. And so when we say that a language is context-free, we mean that there exists a context-free grammar which generates it. And because every one of these rules fits every one of the rules for production rules for a regular grammar fits the rules for the production rules of a context-free grammar, every regular grammar is automatically a context-free grammar. And so the set of regular languages is a subset of the set of context-free languages. I think that's clear. Okay. Okay, so then the context-sensitive languages further continue to loosen the restrictions on what kinds of rules you can have. And so now, we have, this is the only way to write this, it's kind of awkward. Basically take some non-terminal symbol, but now notice that both regular grammars and context-free grammars had the following in common, that you were always replacing a single non-terminal with something. The distinction between those two was what you replaced it with. Here, our grammar can be sensitive to the context in which that non-terminal symbol appears. And thus, we have a sort of production rule which says, okay, it's a lot of notation here, but what this is saying is, dude, take a non-terminal symbol in a certain context, replace that non-terminal symbol with something. So here it's the x which is being replaced with the whatever that is, gamma, and x in the context of alpha and beta should be replaced with gamma. That's what's happening. Okay, so and what are the restrictions? Alpha, and there are very few. Alpha and beta can be actually just anything. So I redo this this notation with sigma union delta star. So they might in fact be complex, strings full of terminals and non-terminals. And the thing that you're replacing it with can be almost anything, but it can't be empty. So, So, okay, not to get too much into the details about this, because this is kind of beyond the scope of this course, but you are not, the context-sensitive grammars don't allow you to just sort of delete a non-terminal in a certain context. That's somehow kind of too powerful because it allows you to sort of delete and create without kind of replacing anything with it. Well, anyway, I'll leave it like that. Okay, so what are some examples of some context-sensitive grammar rules? One is you could have some, okay, this is the simplest possible thing, is you could have something like this, right? Non-terminal symbol x in the context of a and b should be replaced with non-terminal symbol y. But you could also, this is just wrong what I've written here. You could also have a different rule which says in a different context, if x is in the context of a and c, you know, now do something different with x. Now replace it with z. This is the kind of general sort of power that we have. And alpha and beta can themselves be empty, which is to say you can only speak of like left context and right context. So you can say like, you know, if to the left of x there is an a, never mind what's on the right, I don't care. Then replace that x with a z. You can do something like that. And also you can have sort of a more complicated things, right? So okay, I'll just kind of skip all the way to the end now. Now we're saying, okay, x is the non-terminal to be replaced. If to the left of x is a, y, and to the right of x is c, you know, then replace that x with x, b, x, c, or something like that, right? So you can replace now what's being replaced is x is being replaced with x, b, x in the context of a, y, and z. Okay, good. And from the linguistics perspective, it is claimed pretty much accepted by everyone that natural languages like English, natural languages are context sensitive, or at least they are not context free. There are certain grammatical constructions in English which are too complicated. Our ability to perform, I guess this is maybe a little controversial. Once upon a time, everyone agreed with this, and there's always going to be some people who disagree, but back 20 years ago at least, it was mostly agreed upon that due to the ability for natural languages to kind of insert relative clauses kind of arbitrary length into the kind of center of a sentence, and for that to still be totally grammatical and comprehensible, meant that you could not capture that with a context-free grammar. And so, okay, so there's this entire hierarchy. I'm getting a little bit outside my level of knowledge on this, but it's called the Chomsky Hierarchy. It was proposed by Chomsky in 1956, according to the internet, in his attempt to see how much complexity he needed to capture the grammars of English. And this is mainly now considered to be a formal branch of theoretical computer science, computability theory and complexity theory, studying these kinds of things. And if you want to do anything very advanced with theoretical computer science or with compilers or something like that, then it really kind of matters. All right, whew. What are we going to do with this? Not much, but it is nice to revisit some of our examples from the rest of the unit, sort of famous languages which arose and which we attempted to create finite automata for, and couldn't. That's because those languages were not regular, and equivalently, we could not create a regular grammar for it either, because it just wasn't a regular language. So here's an example of a context-free language. And we've seen this before, so context, I don't think people put the dash in there. Context-free language. Okay, so our example, our only example that we'll do right now, this is more for homework, is this language which was sort of the simplest language that we speculated was not regular. And in fact, via the pumping lemma, we proved that this language was not regular. Okay, but this language is describable with a grammar, but not a regular grammar, a context-free grammar. And once you, okay, I just erased it, but you know, consult the notes that you are taking while you watch this video to see that that now with these new rules, I can easily come up with a grammar which generates this language. And okay, it just writes itself, right? Of course, this is going to be AB. I think I need only a single symbol, the start symbol. And well, here's just the grammar. Let's see, do it like this, I guess. Here's the grammar. Well, okay, I need there to be the same number of A's and B's. But now, what made this kind of hard before was that I was always being forced to generate my, I was being forced when I was following the rules of regular grammar to put my non-terminal symbol on the rightmost edge. But now I can just stick it in the middle. And so I think I need just like basically almost just one rule for this language. Replace S with ASB. In other words, just you got your start symbol and just pop an A and a B out on the left and right. Just boop. And now just keep on doing that as ever many times you want. And then boop, 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 and then eventually, you know, just be done. That's it. That is the entire grammar. It's not a regular grammar because the non-terminal symbol is not all the way on the right, but it is context-free, and it just does the job. If you want to make, say, A cubed, B cubed, here's what you do. You start with your start symbol, you replace it with ASB, then you replace S with ASB, boom, boom, then you replace S with ASB, then you replace S with the null string, and done. Alright, so that's kind of nice. And now, here's a way more advanced example that I never appreciated until a few minutes ago. Here's an example of a context-sensitive grammar. Or a context-sensitive language, maybe is the best way to put it. Here's a famous language which is not context-free, which is to say, though the language is easy to describe, you cannot find a context-free grammar which will generate it. And the language is the set of all strings of the form A to the n, P to the n, C to the n, such that n is greater than or equal to 1. Okay, and I have to be honest, I don't think I have any sort of deep intuition as to why this language is not context-free. But I guess you find yourself, well, I don't know. But there is, if you were to take a more advanced course, like a whole entire semester-long course on this, then there's also a pumping lemma for context-free languages. You can prove that every context-free language has a certain property, and this one doesn't have it. Alright, I bet if we were doing this live, you guys would, someone would chime in with some deep explanation of why this is not context-free. But for now, instead, what I will just do is I will present a context-sensitive grammar which generates this language. Okay, here we go. It has 10 rules. Okay, and these are hard. I think they're hard to understand, but I get it now. So how hard could it be? The first thing we do with our start symbol is we make A, B, C. Oh, this is one option. So this is the path we follow if in fact the string is going to have just one A, one B, and one C. So mostly we're not going to use that rule. The rule we're going to, we use this rule either at the very beginning to make the string which is going to have just one A, one B, and one C. And we think of big B as the non-terminal symbol which will eventually be converted into B's. And so this is going to make, applying this rule at the very outset of the grammar will produce the string eventually ABC with one of each. Okay, but what we now do is we sort of linger at the start state applying this rule. Okay, and what does this rule do? Well, it allows you to sort of keep growing the appropriate number of A's. And then eventually, you stop growing A's when you have enough. So as I introduce the rules of this grammar, I think I will show a string generation. Okay, so maybe I want to do this like over here, sure. So let's start with S. And I'm going to make the string A cubed, B cubed, C cubed. Okay, so A cubed, B cubed, C cubed is certainly in this language. Maybe call this like L1, L2. It's certainly in L2. Okay, well here we go. We have our start symbol. Next, we apply rule 2 to replace S with A, S, B, C. Okay, then I apply rule 2 again to grow another little a. And so now this S has just been replaced with A, S, B, C, B, C. And now finally I only need one more A, so now I reach for rule 1, and rule 1 says that this is going to be A, S gets replaced with A, B, C, B, C, B, C. Okay, and now what I have here is a string which has the correct number of A's, and they're all the way on the left, and there are the correct number of non-terminal big B's and non-terminal big C's, but they're all kind of in the wrong place. And so I need to now get them all in the right place. And I think you can see, maybe this is giving me some intuition, though I'm kind of guessing this, of why this is context sensitive, because I kind of want to now be able to replace these big B's with little b's, but not indiscriminately. If I had some kind of rule that said, let big B go to little b, if that were a rule of my grammar, hint it's not going to be, then at this point in the generation I could create strings that were not strings of my language, because it needs to be all the A's followed by all the B's followed by all the C's. Okay, so now what we need to do is like methodically transform all this string of BCs into BBB, CCC. Okay, and what you kind of wish you had was a rule that said, yo, I want to just make, what I really need to do is I need to swap the B's and C's, right? I need to move all the B's to the left, and I need to move all the C's to the right. So what you want to do is, you basically want to perform a whoop, whoop, whoop. I'm like, okay, I'm like such a not computer scientist that whatever that is, some kind of bubble, swappy, sorty thing. There's definitely a term for it I don't remember. But what you want to do is, yeah, what you wish you had was a rule that said, let CB go, let CB go to BC. Okay, but that is basically what we're going to do. And first I'll just show you, I'm now going to follow that rule. So I'm going to, well, let's just suppose I had a rule like that. Then what could I do? Well, then I could just start moving these things. I don't think it matters how I do this. I haven't really thought this through super carefully, but right here, this CB could be replaced with BC, and then CBC, and then I just do that like 2 more times or something, right? So A, big B, now this BC swaps, or this CB swaps and becomes a BC, and now I do it 1 more time. Okay, so this is the level of detail that I plan on showing in this video, because this is just a sort of survey of this material. But the reason why I'm sort of dancing around this is because this is actually not an allowable rule of my grammar, because part of being context sensitive is that you can replace something, a non-terminal, with something else in a certain context, but you can't like disturb that context. So this rule is sort of telling me, well, this is just not an allowable rule of my grammar. But there's like a kind of a workaround, which was not obvious to me at all. I mean, I just got this from Wikipedia. But the workaround says do the following. In a kind of like little dance, I'll do this in purple, I propose rules 3 through 6, which replace CB with CZ, CZ with WZ, WZ with WC, and WC with BC. Okay, so, oh man, what is going on here? Well, I'll sort of make like a kind of blue box or something to try to explain this. Rules 3 through 6 just do what you want this rule to do. And how does that work? Well, it's like you have, let's see, you have CB, so CB, and then you replace it with CZ. So what have you really just done is you've sort of pivoted around this C, right? You've said, okay, anytime you have non-terminal C, sorry, I did that wrong. It's the other one I'm sort of pivoting around. So, sorry. What I mean by that is it's B is the non-terminal which is being replaced. You should think of rule 3 as saying, if you have a non-terminal B with a C to the left, then replace that B with a Z. Okay, and then what does the next rule say? It says that you can go from CZ to WZ, and that should be interpreted, if I'm thinking about this correctly, as saying, if you have a C with a Z to the right of it, well, replace that C with a W. Okay, so in each case what I'm doing now is I'm circling, this is just an invented notation, I'm circling the non-terminal, which is the true sort of subject of that production rule, so to speak. And then finally, no, not finally, then WZ goes to WC. So now I say, okay, now Z, non-terminal Z, with a W on the left should be replaced with a C. And finally, this WC gets replaced with BC, and really we should be thinking of that like this, as saying if there's a W with a C on the right, then replace that W with a B. And so via 1, 2, 3, 4 moves, these 4 rules conspire to essentially allow you to just swap BC and CB and BC like that. Okay, so I kind of made like a macro out of that 4-step thing, and I applied it 1, 2, 3 times to put all the things in the right order. Okay, and now we need the rules to just like finish it off, and there are 4 of them. Make sure I understand these rules. They all now just stick the B's and C's in where they need to go. But whatever rule you make that's going to replace these big B's with little b's, you need to make the rule specific enough that it doesn't allow you to replace them too early when the big B's are still in the wrong position. So I need these rules to be powerful enough to enable me to replace the big B's with little b's sort of now when we're done, but not so powerful that they will let me replace the big B's with little b's earlier on in the generation when the B's aren't in the right place yet. Yeah, this is a pretty good explanation, I think. Okay, so I have this rule that says a big B goes to little a little b. Okay, so this says, dude, if you have a big B, then you should certainly be free to replace it with a little b if it's just to the right of a little a. Or, more in the language of the grammar, if you have a big B with a little a to the left of you, then it means that B is like kind of where it should be, right? That's where big B's belong. Just one place that a big B could belong is just to the right of a little a. And so, boom. So you just do that. Okay, all that does is this rule 7, if I'm doing this correctly, performs one function. It allows you to convert the first big B to a little b. Okay, so I apply that rule now. Okay, And what next? There's another rule that says, this is rule 8, which says a little b, big B, goes to little b. Okay, this says that you may replace a big B if there's a B to the left of you. So in other words, you can sort of be basically guaranteed that this big B is in the right place if there's just if it's adjacent to some little b's that already exist. If you've already generated the string there, you can just drop more b's there at any time. So now we apply that rule, I guess, twice, right? So we get a, little b. I convert that big B to a little b. And then one more time, a, little b, little b, big C, big C, big C. Okay, and now I need to have two more rules that are very parallel to the two previous ones. I need to replace my big C's with little c's, and there are sort of two cases. It should be allowed to replace a big C with a little c when that big C is adjacent to a little b. So like now, so I use rule 9 always precisely once in any generation, I believe. So this is A, B, B, and this C gets replaced with a little c. And now I have two non-terminals left, and for this, I bet you can just sort of guess. The rule that you would need is little c, big C goes to little c, which is to say, if you have a non-terminal big C with a little c to the left of you, then it's in a safe spot and you can replace it. So now I use rule 10 twice, cha, and one more time, cha. And that's it. This is A cubed, B cubed, C cubed. Okay, that is an example of a context-sensitive language or context-sensitive grammar, and the increased power that it has to produce strings of sort of more complicated languages. But we're not really going to do anything with that. All right, and then we're going to do basically one more thing, because you might be thinking, well, if regular languages can be described with regular grammars, but maybe more sort of fluently described or thought about differently with finite automata, is there some kind of a computational theoretical machine analog to these other grammars? And the answer is yes. There is this thing called a pushdown automata, or a pushdown automaton. The plural is pushdown automata. And this is a more complicated and more powerful kind of theoretical machine, which is exactly analogous to the finite automata for regular languages. And these machines are precisely powerful enough that they can recognize any context-free language. And so for any context-free language, there is a